Hello. So in the last video, I described instantaneous velocity, and that was determined by the slope of the position versus time graph. Today, in this video, I want to analyze the graph of velocity versus time. So to do that, let's imagine a scenario where things are pretty simple. So let's say, I don't know. Let's imagine that something starts at position 0, and then in time it kind of moves steadily to the right. So 1, 1,000, 2, 1,000. So let's say over 2 seconds, I traveled 2 meters. So we could do like before. We could make a graph of position versus time. And if we did that, I would say, well, okay, I said I was going to define the beginning point to be 0. So I started here. And then at 1,002, so 1 second and 2 seconds. And then after 2 seconds, I had traveled 1 meter, and I'm assuming that it was a steady motion. And so I was here, so I'm going to draw a line. I should have something like that as my graph of position versus time. And this is what we did last time. Just to review, last time we determined that the instantaneous slope of the position versus time graph gives us the instantaneous velocity. Well, in this case, the slope, it's a line, so the slope is the same forever. Okay, so the instantaneous velocity, or just the velocity, because I'm tired of saying instantaneous over and over. The instantaneous velocity is the slope of this curve, and because it's a straight line, that's actually the same as the average velocity, or the average slope, and that's just going to be the change in the height or the change in the base, the run, rise over run. So that's going to be the change in x, which would be 2 meters, divided by the change in time, which is 2 seconds. So that'd be 2 meters over 2 seconds. That's just 1 meter per second. Now, I use the formula for average velocity, but really I was wanting the instantaneous velocity, and that's okay as long as this is a linear curve. So that's why I do that. Very good. So at each moment, the slope is 1 meter per second. So the slope here is 1 meter per second, 1 meter per second, 1 meter per second, 1 meter per second, 1 meter per second. Okay. So let's turn that around. Let's assume that we know that the velocity is 1 meter per second for 2 seconds. Let's see what we can determine. So for 1 second, here I have 2 seconds. And the velocity is, let's just go here and we'll say 1 meter per second. And let's kind of plot points to see how that would go. Well, the velocity right here, the slope right here is 1 meter per second, 1 meter per second, 1 meter per second, 1 meter per second. So if I was to plot this, I'd have 1 meter per second, 1 meter per second, 1 meter per second, 1 meter per second, 1 meter per second for all times like that. And I would just have a curve, if I connect things up, it would just be a flat horizontal line. In the velocity versus time graph is horizontal. The position versus time graph is sloped. Okay? So once you have an instantaneous velocity, a velocity that's defined and associated with each moment, then you can make a graph of it. This one's particularly easy because the slope is constant. The velocity is constant through the whole interval. Here's a curiosity. We've already talked about slopes on this graph, and the slope of this one's 0. We'll come back to that one, what that means later, the slope of the velocity versus time graph. But in addition to slopes, there's another geometric quantity which kind of presents itself. You could also think about areas. In particular, you can think about areas under the curve. Okay, so the area under this curve, if I kind of shade that region in, might be an interesting thing to determine. And when I say area under the curve, I mean the area from the graph of velocity to the time axis. We'll talk about something, I'll show you something else in a minute. But okay, well, how would you find the area? Let's do that. So the area, I'll put under in quotes. Velocity versus time. Well, to do that, I would say, okay, well, it's a rectangle, so the area would be base times height. So the base is 2 seconds. Two seconds multiplied by a height of 1 meter per second. Okay. The base has units of seconds, the height has units of meters per second. I know it's a little weird, but okay, not too bad. And if you do that, seconds will cancel, you'll be left with 2 meters. Now, that's kind of an interesting thing. 2 meters. It's a curious thing. It's not a random number. It's not a random result. In fact, you might notice that 2 meters is in fact the change in position from time 0 to time 2 seconds. So if we started at 0 after 2 seconds, it's up here at 2 meters. Delta x for my position graph is this same result. And that, in fact, is always going to be true. So I'll go ahead and tell you, I will claim, I guess without proof, really, probably have to have a calculus to really prove it, but it always works out that way. The area, I'll put under in quotes, velocity versus time gives the change in position. The area under the velocity versus time graph gives the change in position. And I drew this for a nice simple rectangle. It's going to be true always, even when you have weird bendy shapes. The math and the equations can get a little complicated, but the geometric property remains true. So that's a really important thing for us to remember. Let's see what happens when we have a negative velocity. Okay, so let's imagine a situation where we start, let's define this to be 0, and I'm going to move to the left. So I'm going to do this, it's really going to be a similar motion, just reverse. So I'm going to say 1, 1,000, 2, 1,000. So I'm going to assume that I moved steadily to the left. So I'm going to have a negative velocity because I'm headed in the negative direction. And it's going to be steady. So it's going to be a steady velocity, so a constant velocity. So if I were to graph x versus t, I said, now, okay, I have to be a little careful here. I said I started at 0, I moved 2 seconds. And it was -1 meters, and then I was at -2 meters. So after 1 second, so I started at 0. Oh, I'm using green for these, I apologize. Switch back to green. I started at 0. And then after 1 second, the position was -1 meters. And after 2 seconds, the position was -2 meters. And we assume we could have measured, or maybe we did measure all the positions in between. So we can go ahead and dot that in. Okay. Notice the slope is negative. It's negative for all the points, indicating that I was always moving in the negative direction. My velocity was always negative. And the slope, because this is a line, the slope is constant throughout. And it is the change in position over change in time will be -2 divided by -2 will be -1. So the slope is -1. So the velocity is -1 meters per second. That makes sense because I started at 0 and I walked to the left. Now, I can do the same thing that I had before. I can graph velocity versus time. So I'm going to do that. So I make a graph. Now, my velocity is always -1, so my graph is actually going to be into the negative direction. So I have velocity, I have time, 1, 2. Apologize. Okay, and then my velocity is going to be -1 meter per second, and it is going to be constant for all time. So it could be, so -1, the slope here is -1, -1, -1, -1, -1, -1. The velocity is always -1. So if I were to plot measurements, I'd have -1, -1, -1, -1, -1. It's always -1. And we can connect the dots here. So we measured all these points. Just be a horizontal line. The slope would be 0. Slope of the velocity graph is 0, but in this case, but the slope of position is -1. Now, let's measure the area under the curve. Now, when we say under, we always really mean the area between the curve and the time axis. And here's the thing. When you took geometry, in high school maybe, or in other classes, you always talk about areas as if they're positive things. But here, what we're going to say is that if the graph is below the time axis, it contributes a negative, it's like it has a negative height. So that's going to mean the area that we get ends up being negative. So if I evaluate the area under this curve, that, I'm going to say that the height, quote unquote, of this rectangle is negative because it was a negative velocity. It was below the time axis. And I'm going to say the area is base times height. Well, the base is 2 seconds times the height. Well, the height is -1 meter per second, giving me area of -2 seconds cancel, and -2 meters. And sure enough, if you go back to our original graph, the change in position over the first 2 seconds is -2 meters. The area under the, I'm going to go under, when I say under, I mean the area between the graph and the time axis. The area under the velocity versus time graph is -2 meters. This -2 is not an accident. It's the same as the change in position over that same time interval. Right? So I've stated this for nice, simple, linear position versus time graphs and nice rectangular shapes here in the velocity versus time graph, but the result is general. It's always true. So I'm going to write, so I'll give you an example of what you could have. You could have a more complicated motion, and indeed we will do some examples like this. have velocity versus time graphs, which were complicated. They can look like this. So I'm graphing velocity, not position, velocity versus time. And you could have graph, let's mark some time here first. Okay, 1 second, 2 seconds, 3 seconds, 4 seconds. And we could have velocities, let's say we start at 0 velocity. Okay? And then let's say, oh, we gained velocity up to 1 meter per second over 1 second. And then we kept that constant value. And then we went down to 0. Okay? And then our velocity actually went negative, down to -1. Okay? So it went down to -1 meter per second. What would this mean? Well, this would mean that you started at rest. Okay, so you started at rest, and then we built up speed to reach, after over 1 second, to reach 1 meter per second positive. So that would be 1 meter per second to the right. So we start slow, start close to 0 velocity, and then we increase, and now we keep a constant speed, and then we would start to slow down and come to a rest at some point. I'm off the screen here. And would stop. The velocity would be 0, and then our velocity would change signs. So we'd get to 0, and then we would start moving and speeding up in that backwards direction. All right, so it'd be something like this. We'd start here, we would start at rest, and it'd be slow, constant, slow down to 0, and then change directions and come back. It's that kind of a motion. That's what that would mean. What if I wanted to find the change in position over some interval? Well, and you get to choose. So if it was to find the change in position over the first interval, you would find the area of this first, if it's to find delta x for the first second, you would find the area for the first second. Call this delta x from 0 to 1. And then you could find, if you wanted to find the change in position over the next second interval, you could use the area of this square or this rectangle to find delta x from 1 to 2. And then if you wanted to find the change in position for the next interval, you could do that. You could find the area of this triangle to find delta x from 2 to 3. Each one of these would have been positive, because you remember when I did this, I started at rest and I sped up, I gained position, I reached constant velocity, I kept gaining position, and then my velocity decreased, but I was still moving forward to a stop. When I got to here, that's when my velocity was 0, and then after I reached that stopping point, my velocity was negative, and I moved backwards. So I would have had a negative displacement over this interval, and sure enough, the area here would be negative. This would give me delta x from 3 to 4. And if you wanted the total displacement, you would add up all the separate displacements. If you just want some portion, you just keep that part of the area. And that's how you could use the area to find changes in position. So in the last video, I made the following kind of table here where I said x versus t. And to go this way, we use the slope, and that gives us velocity. Now, over here, we're going to have velocity versus t, and we can go this way using the area, and it doesn't quite give us x, it gives us the change in position. It gives us delta x, the change in position. But we can go from position to versus time to velocity from looking at the slope, and we can go from velocity versus time back to position almost by using the area. It doesn't quite give us position, it gives us the change in position. But it's morally, you're working your way backwards. Okay? So that is how we can graphically go from position to velocity or from velocity back to position. So in the next video, I'm going to go through an example doing exactly this, and we will just work out the numbers. Okay?